Hello everyone. Through this video, we are going to discuss some additional questions on the first exercise in the chapter of real numbers. So here goes the first question. Prove that if x and y are odd positive integers, then x square plus y square is even but not divisible by 4. Now the first and foremost thing that we have to notice here is what? X and y are odd positive integers, and we can consider these odd positive integers in the form twice m plus 1 and twice n plus 1. So let us consider in that way first. Let the two odd positive integers be taken as capital X is equal to twice m plus 1, and let's mark this as 1, and y is equal to twice n plus 1, where we mark it as 2. After this, we have to find out the value for x square plus y square. Ultimately we have to determine whether x square plus y square is even or not, and whether it is divisible by 4 or not. Let us check it out. So here in this case, squaring and adding. Of course, I have to square x and y so that I can get the term x square plus y square. And along with that, their right hand sides will also be getting squared, and then we can add it. So I can write here squaring and adding. 1 and 2. What do I get here? X square plus y square is equal to their corresponding right hand sides. When squared, we get this result, twice m plus 1 whole square plus again twice n plus 1 whole square. Let us break it up. X square plus y square is equal to, for this part we can use the formula twice m whole square. I'm using the formula a plus b whole square. So this is a square, that means 2m whole square, twice ab will be twice m into 1 plus 1 square. While for the second case, for this term twice n plus 1 whole square, I can get here twice n whole square plus 2 into twice n into 1 plus 1 square. After that, what can we get? X square plus y square is equal to, when splitted and simplified, I get here 4m square plus, in this case it is 4m plus 1 plus, in this case I get 4n square plus 4n plus 1. After that, what do I get? On the right hand side, left hand side will remain as it is. On the right hand side, I can take common 4 in all these 4 cases. Am I right? So I'm going to take common 4 in all these 4 cases and arranging them properly. Within the bracket I get m square plus n square plus m plus n plus 1 plus 1, I get here 2. So from these two parts, what do I get? X square plus y square is equal to 4q. Suppose I consider this whole thing as an integer q plus 2, where I can write here where q q is equal to m square plus n square plus m plus n. So after this I can write x square plus y square is equal to, what do I means in what way can we proceed here? We can take common 2. I get here 2q left within the bracket, plus in place of this 2 I can put 1. So it is very clear that the quantity which I get on the right hand side is a multiple of 2. 2 into something means that is a multiple of 2. That is why, since this is a multiple of 2, it means what? The term present on the right hand side is divisible by 2. The term present on the right hand side is divisible by 2. Therefore, what can we conclude? I can conclude in this way that x square plus y square is even. So the first part is already proved, means in the first part what we had to show, in the first part in the question we had to show that x square plus y square is even, and that part already we had proved. Now coming to the later part, actually we have to show that the quantity which we get for x square plus y square is not divisible by 4. So let us check that part next. So coming to the second part, I get here, but x square plus y square is equal to, we got 4q plus 2. That means we cannot take common 4 here. That means in this case on the right hand side 4 is not coming as a factor of both these two terms. Therefore, what conclusion can we draw here? This quantity x square plus y square is not divisible by 4, because the quantity present on the right hand side cannot be expressed as a multiple of 4. Therefore, what conclusion can we draw here? X square plus y square is not divisible by 4, and that is what we had to prove. So the final sentence you have to write in this way. Hence, if x and y are odd positive integers, then x square plus y square is even but not divisible by 4. So coming to the next question, this is the next important question, question number 2. This is question number 2. What is asked here? Prove that n square minus n is divisible by 2 for every positive integer n. So I consider that any positive number can either be even or odd. Yes or no? For even number, when the integer is even, it follows the format twice m, and when it is odd, it follows the format twice m plus 1. So two cases we are going to consider here. Positive integer, positive integer includes both even and odd numbers. Therefore, once this case we shall consider, and once this one we are going to consider. So what in the solution part, what we are going to write? First of all, we shall start our solution in this way. We know that any positive integer small n, say we are considering any integer n, is either even or odd. So why we are writing this? Because any number, I mean any integer, say 2, 3, 4, 5, 6, any integer if you consider, we can find the integers either as a number which is divisible by 2 or as a number which is not divisible by 2. Suppose in the list of integers 2, 3, 4, 5, 2 is divisible by 2, then 3 is not divisible by 2, therefore it is odd. Again 4 comes, 4 is divisible by 2, therefore it is even. Then again 5 comes, it is not divisible by 2, therefore it is odd. So in all these cases, in case of all positive integers, what do I find? We find that the numbers are either divisible by 2 or not divisible by 2. When the number is divisible by 2, they are called even, and even when the numbers are not divisible by 2, in that case they are known to be odd. Therefore, of course, two cases will come. So what did I write? We know that any positive integer n is either even or odd and can be of the form n is equal to 2q or n is equal to 2q plus 1, q being any integer, q being any positive integer. I'm writing here positive integer because in this case we are dealing only with positive integers. That is why q has to be positive to get value of n as positive. So two cases will of course come here. So I get case 1. Let's delete this part. So this is case 1. So for case 1, I can write when n is even, that is n is equal to 2q. What do I get? Let us scroll it down. So after this we get what? When n is equal to 2q, actually our intention is to find out value of n square minus n, and we have to show that it is divisible by 2. So using these two cases, let us find out what is the value of n square minus n. So here I get n square minus n square minus n is equal to, in place of n we can put the value twice q, it is getting squared, minus in place of n what do I put? 2q. Let us break it. So when this term is simplified, I get a result 4q square minus 2q. So in these two cases, can I take common 2? Yes, of course I can take common 2. Within the bracket, what is left behind? 2q square minus q is left. So I can further reduce it to the form twice m being equal to 2q square minus q. So this will imply what? That is n square minus n is equal to twice m, as we can express it as multiple of 2. I mean we are in a state in which we can express n square minus n as multiple of 2. It means what? This is an even quantity which is even. So case 1 is already solved. That was what we had to prove. Coming to case 2. In case 2, we have to consider n as an odd number. That means we shall be writing when n is odd. N is odd, that is n is equal to 2q plus 1. I mean the second case we are considering here. Then let us find out what is the value of n square minus n. In the respective places of n, I am going to put the value 2q plus 1. For the first place, it is getting squared followed by this minus sign. Again, in place of n, I am going to put 2q plus 1. Let's break it again. The first quantity will follow a plus b whole square formula. And I am going to get here 2q whole square plus 2 into 2q plus 1. That means this part is twice ab form. Plus b square is 1 square. Minus, in the second part when brackets are removed, I am getting the form minus 2q minus 1. Again, in the next step, I shall get 4q square plus, after this 4q plus 1 minus 2q minus 1. So plus 1 minus 1 got cancelled. I get here 4q square plus 4q minus 2q. The result I get as 2q. When I take common 2, I shall get 2q square plus q, which can further be expressed in the form twice m, where m is equal to 2q square plus q. So again, in this case also, it is very clear that n square minus n is expressible as multiple of 2. So I can write here, that is n square minus n is equal to twice m, which is even. That is what we had to prove. So in both these two cases, I mean in case 1 also we got the result. We got the result as multiple of 2. I mean n square minus n is expressible as 2 into something. That means this is an even quantity. While in the second case also, I am getting the value twice m. That means this quantity n square minus n is also expressible as 2 into something. That is why in this case also, I mean in case 2 also, n square minus n is an even quantity. So the final line we can write in this way. I mean the concluding line should be like this. Hence, it is proved that n square minus n is divisible by 2 for every positive integer n. For every positive integer n. So that's the answer. This is question number 3, which is another important question. Let us see what does it say. Show that n square minus 1 is divisible by 8 if n is an odd positive integer. Actually, we know one thing, that when n is an odd positive integer, odd positive integers always take the form 4q plus 1 or 4q plus 3. Actually, I am taking here 4 because any number which is divisible by 8 is also divisible by 4. So, given, we shall be writing here, given n is an odd positive integer. We know that, after this we have to write, we know that any positive odd integer takes the form 4q plus 1 and 4q plus 3 for some integer q. Now in this case there will be a question, why we have considered 4 and not 2? Because in case of odd integers there is only one form taken. If I consider 2q plus 1, and when I put this value in this expression, let us see what result we get. 2q plus 1 whole square minus 1. Let us break it. 4q square plus 4q plus 1, sorry, it should be equal, minus 1. 1 minus 1 got cancelled. 4 comes as the common term. So we cannot show here that this number is a multiple of 8, which further does not allow to show that this quantity is divisible by 8. That is why this is discarded. We are taking 4 and not 2. So coming to the later part, two cases again will arise here. That is what? 4q plus 1 and 4q plus 3. So case 1 when n is equal to 4q plus 1, we shall get n square minus 1 is equal to 4q plus 1 whole square. Actually I am writing 4q plus 1 in place of n, minus 1. What result do we get? 4q whole square plus 2 into 4q into 1 plus 1 minus 1. 1 got cancelled. While breaking it, I am getting 16q square plus 8q, from where we can take common 8, and within the bracket I shall get 2q square plus q, which can further be expressed in the form 8m, where m is equal to 2q square plus q. So it is very clear that for this value 4q plus 1, n square minus 1 is divisible by 8. So I can conclude for case 1, therefore clearly n square minus 1 is divisible by 8. So coming to case 2, in case 2 again the other case we have to consider, the value n is equal to 4q plus 3. So let us check what answers we get. I have to put these things in place of n square minus 1 to show that it is divisible by 8. So n square minus 1 in place of n I am putting 4q plus 3. It is getting squared minus 1. Then after when broken into the form a plus b whole square, I get here 4q whole square plus 2 into 4q into 3 plus 3 square minus 1. Breaking it, I shall get 16q square plus, on this part, 2 into 4 it is 8, 8 into 3 it is 24, 24q plus 9 minus 1. So on reduction I am getting 16q square plus 24q plus 8. So can I take common 8 here from all these three parts? So I can write here 2q square plus 3q plus 1, which further gives us the form 8m, m being equal to, where m is equal to 2q square plus 3q plus 1. So what we wanted to prove, we had already proved, because in case 1 also we got that n square minus 1 is divisible by 8, while in case 2 also we got the result 8 into something for n square minus 1, which shows that it is further divisible by 8 in case 2 also. So final line we can write in this way: hence clearly n square minus 1 is divisible by 8 if n is an odd positive integer. N is an odd positive integer. That was what we had to prove. So that's all. Today through this video we had discussed 3 additional important questions for the first exercise of real numbers. In my next videos we are going to discuss some more additional questions. Thank you.